So I looked up linear programming on ChatGPT, and we seem to differ a little bit in terms of the early roots of linear programming. They seem to start it here in around 1947. That's great, but some of the applications that I'm familiar with came from World War II. We were trying to fight a world war, and we want to get supplies into place. We need to make production, etc. But you're working under constraints. You can't always, throw as much manpower or as much resources at a problem as you'd like. And that's where the subject of linear programming, to me, really kind of first develops. Now, I'm going to give you a completely made-up example that tries to show you some of the rudiments of linear programming without having some really strange numbers or anything really too crazy to work with. And that is my side hustle. Farmer Jeff has 20 acres of land to plant. All right, so great. How are we going to allocate that land? Well, he could plant either soy or corn on his land. So the number of acres that he devotes to each of those crops is going to be either X for the number of acres of soy or Y for the number of acres of corn. That's great. You got those 20 acres of land to plot. But that actually is a constraint on what you plot. I mean, to make the most money, you want to plant as much land as possible. But one of the constraints that you're working under is this, and that is X plus Y has to be less than or equal to 20. You can't plant an infinite amount of stuff. So, okay. Now, soybeans need 4 bags of fertilizer per acre, and corn needs 3 bags per acre. Jeff has 72 bags of fertilizer available. So again, that's kind of a constraint on your work. You can't just, plant all of one crop because you might run out of bags of fertilizer. So let's see about another constraint here. It takes 3 bags per acre of soy, and it's 4 bags per acre of soy, and corn needs 3 bags. So it's going to be 4x plus 3y, and we got a maximum of 72 bags available. Okay, so 72. All right. Now there's a couple other constraints that are not really written here, but that are kind of implied about this problem. And let's try and understand what those constraints are. We're planting acres of soy and corn. What's the minimum that we can plant? At the very least, you can plant this many acres. What would that minimum be? X has to be greater than or equal to, or Y has to be greater than or equal to. What number? What's the least that you could plant? 0. And let's start out with these two constraints and graph them. So we got those two constraints. Let's put them on Desmos. And those two constraints are right here. X is greater than or equal to 0, and Y is greater than or equal to 0. Now, what do you notice when I highlight both of those inequalities? What's of interest to us as a mathematician?
The first quadrant.
Yeah, the first quadrant. They overlap in the first quadrant. So, okay, great. They overlap in the first quadrant. That means our solution's in the first quadrant. If you look at your handout, that's all I've graphed here is the first quadrant. That's all I need. So, okay, let's go back to the first quadrant. I'm going to shut these off. I'm going to understand that my solution is going to take place in the first quadrant. So the next thing we need to do is we need to graph each of these lines. So the corresponding equations. So I'll start out with this one, x plus y. Actually, let me put it up here. X plus y equals 20. So if I put in x equals 0, what would I get for y? Yeah, 20. If I put in y equals 0, then I would get 20 for x. So if you look at that, that looks like these points here and here. Let me kind of color code this a little bit. We'll do that one in a very manly salmon. So that's this line right here. And I don't think I drew that too yet. Yeah, that's not too bad. Okay, so that's one line. And let's draw our other line. Our other line comes from this inequality. That's going to be 4x plus 3y is equal to 72. I think we're going to have to work a little bit harder, not a lot harder, but a little bit harder to come up with the points here on this one. So this time I'll use green. If I put in an x equals 0, that gives me 3y equals 72. Who's quick with the arithmetic? 3y equals 72. 72 divided by 3 is 24. Well done. And then the next one, if I put in a y equals 0, I get 4x equals 72. 72 divided by 4 is 18. Well done. And you can see those points up here. Here's 0, 24. Here's 0, 18. I'll put that one in green. Okay. So let's see here. Now we need to decide where we're going to shade each of these things. So let's do that. And for that, I'm going to need a test point. Now, for myself, my favorite test point when I'm working with these inequalities is this, 0, 0. It's just easy to plug in 0, 0. And since 0, 0 is not on either line, then we're okay to use that for both lines. Let's start with test 0, 0 in this inequality. That is x plus y is less than or equal to 20. So 0 plus 0 less than or equal to 20. True or false? Yeah, that one's true. How about our other one? Let's test 0, 0 again. This time it's going to be in the inequality 4x plus 3y is less than or equal to 72. So is 4 times 0 plus 3 times 0, is that going to be less than or equal to 72? Well, what do you get on the left-hand side here? 0. 0 less than or equal to 72, is that true? Nice. Now, let's keep in mind a couple things here. You have these natural constraints, which means our solution is strictly in the first quadrant, because you're not going to find x and y greater than or equal to 0 other than the first quadrant. So that's as far as we're going to pay attention. And then I've got to figure out, well, if I shade underneath this line and underneath this line, where do those shaded regions overlap? And try and use your mind's eye to try and envision where those shaded regions are going to overlap. Because where they overlap is going to represent all the possible combinations of x and y that are going to satisfy our problem. So let's do it dramatically over here. We've got our two lines. Oops. Our two lines here. And if we shade underneath one line and shade underneath the second line, can you see where those shaded regions are overlapping? You're not going to count this little piece here and this little piece here. In fact, right here, there's your solution region. Let me get rid of these two now. That's what's called your solution polygon, or your feasibility region if you wanted that, to say it that way as well. So let's kind of color that region. So that's going to be everything in here. So this is your feasibility region. AKA solution polygon. Well, the solution polygon, I guess it'd be just the, well, yeah, I guess it'd be solution polygon. So this is all the combinations of crops that don't blow past our constraints. We're not planting too many acres, and we're not using too much fertilizer. So the question becomes then, it's like, well, all right, well, which one of these combinations do I want to use? Which one's going to make me the most profit? It's a good question. Now, I haven't talked about our profit function, but our profit function is outlined at the bottom of this. If an acre of soy is worth 220 and an acre of corn is worth 190, how much of each should we plant to maximize the profit? Well, it's a good question. So we've got this function, and I'm going to write it as P of X and Y. P for profit, depends on X and Y. And we get 220 per acre of soy plus 190 per acre of corn. So this is your function that you want to try and optimize, your objective function. Objective function. Typically speaking, depending on the problem, you're either going to want to try to maximize this or minimize this. There's just one problem. Take a look at your feasibility region. How many points are there in your feasibility region?
Unlimited.
Yeah, an infinite number. So what we'll do is we'll divide up the work. Left half of the room work on the bottom half. No, never mind. That would still take a little bit too long. But there's good news. There's really good news. And that is you don't have to test all of these points. Instead, all you have to test is these corner points, the vertices. There's a nice theorem in linear programming that says the maximum or minimum is going to occur at these corner points. You don't have to test an infinite number. In fact, all we really have to test is 4 points. So, okay. Question is, what are those 4 points? Now, good news for you. Earlier, you had the wisdom to plot points using your x and y intercepts, that is, setting x equals 0 and y equals 0. So I already know that this point has coordinates of 0 and 20. How about down here? What are the coordinates of this point? 18 and 0. Good. This one is 0 and 0. Now you might notice that I kind of left that one off of my list here. Can anyone suggest a reason why? Could this be a maximum? No, if you're not planting anything, you're not making anything. So, okay. And the last one is this one. How are we going to figure out what that point is? Now, your graph is actually good enough that you kind of eyeball it. But, you know, on an exam, might not give you a graph that's quite so nice. In fact, you're probably going to have to graph that yourself. So, how can I find the maximum for that one? Or, excuse me, not the maximum, but the point of intersection. What if I was to give out bonus points for the correct answer? Oh, Ethan, hand up quickly. Yes, go ahead.
You could use substitution in
Yeah.
those system equations.
Yeah, you've got a system of equations here, right? You've got x plus y equals 20. You're going to solve at the same time as 4x plus 3y equals 72. So, boy, you've got elimination, you've got graphing, you've got substitution, you've got Cramer's rule, you've got Gaussian elimination, you've got inverse matrix. There's no shortage of things that you could use to solve this system of equations. But let's just eyeball it. What does it look like? What coordinates does it look like there? Blake, you got them? Yeah, it looks like 12 and 8. Now, how can we be sure that 12 and 8 is correct? I mean, this is just kind of freehand drawing here a little bit. How could you make sure that 12 and 8 is correct?
Plug it in.
Yeah, 12 plus 8 is 20, so it works in the first one. 4 times 12 is 48, plus 3 times 8 is 24, 48 and 24. Yeah, it works. So Blake's is exactly right, 12 and 8. So we need to take these points, at least these 3, and dump them into this function, which is what I've done down here. Now, I could do that by hand if I really wanted to, but I don't. Instead, let's go back to Desmos. One of the cool things you can do on Desmos is you can define a function. And I didn't really, use rocket science to define this. I just said, all right, well, P of x comma y equals 220x plus 190y. And then I can dump in points like 0, 0. And of course I get 0. 0, 20 gives me 3,800. That one's already on your sheet, I think. Yeah, 0, 20 is there. The one that's not there is this one, 12 and 8. And all you're doing is taking 220 times 12 plus 190 times 8. You get 4160. So let's write that one down. 220 times 12 plus 190 times 8 equals 4160. Nice. And that one happens to be your maximum for this problem. Nice. You do have a minimum at 0, 0. P of 0, 0 would be 0. So that would be your minimum. Not that we're trying to minimize something, but you could. Now, a lot of times in these problems, it works out that this point is the point of interest. But I could change that. If the price of soy and the price of corn changed, then your maximum could be a lot different than what we chose here. Right now, this is kind of a nice hybrid solution because what you're doing is you're using all your acreage and all your fertilizer. Here, you're just saying, all right, let's plant everything soy. Here, you're saying, let's plant everything corn. Neither of those solutions work. Well, I mean, they work to an extent, but you're making more money here than you are down here. All right. So that's kind of a lot to absorb. Let me recap a few things in this. The first thing you have to work with is setting up your constraints. If they're not given to you, you're going to have to figure out what those are. So determine your constraints and then graph the constraints. That was this part down here. You need to determine your feasibility region. What values of x and y can actually be used to maximize your objective function. So once you graph those constraints, you're going to test points and decide where you want to shade. That outline gave us our feasibility region or our solution polygon. And from there, we took points from the corners or the vertices and plugged them into our objective function to try and find whatever maximum or minimum we needed. So, yay. That's it. All we have to do on that one. Now, not every problem is going to be quite so long, but that's kind of the gist of these types of problems. In World War II, for I think 18 months, Berlin was supplied. Berlin was in the Russian zone. It was cut off from all kinds of supplies. It was literally surrounded. And the only way we could get supplies into Berlin was with a massive airlift campaign. And you had to maximize the stuff that you took over there, subject to the constraint that you only had so many pilots and so many planes. So that would be another application of linear programming. Okay. Any comments or questions on this first one? Yes, ma'am.
So just to make sure, like the min max are always going to be in the feasibility.
They're always going to be one of the corner points of this feasibility region. And the nice thing is that by only having to look at the corner points, there's going to be a handful or so of points you have to test in the objective function. Otherwise, if we didn't have that theorem, it'd take quite a while to test all of these points. So fortunately, we don't have to. Appreciate the question. All right, let's ease into things with example A on our handout. And for this one, I've already given you the feasibility region. So, and you've got this objective function. Now let me rewrite that as maybe m of xy equals 250 x or 250 minus x minus y. 250 minus x minus y, so not a really dramatic function there. Let's determine our corner points here. What are the coordinates of each of these points going to be? Well, let's see. The first one up here looks like 0 and 5. And another one at 0 and 2. How about this last one? What's the coordinates of that one?
1 and 0.
Yeah, 4 and 0. So what we're going to have to do is plug in each of those points into our objective function and see what we get. So let's see, we've got 0, 0, 4 and 5, 2 and 0. Okay. 0, 0, 4 5, 2 and 0. So that gives me 245, 248, and 246. Now you're asked to determine the maximum value and the minimum value. So let's take a look here. What's our maximum value? 248. That's your max. Lena, what's the min? Yep, 245. So, min and max. I'm afraid that's it. Dan, you want me to make that harder? You look disappointed. Like, oh my gosh, is that it? Really?
I'm having fun.
You're okay with that?
Yeah.
All right. I appreciate that. Going with the flow this morning. Thank you so much. That's it. We're trying to maximize that. Now, fortunately for us, we already had that one graphed, and it was easy to pick up the points, our corner points, our vertices of our feasibility region. But yay, that's it. Let's do one that's a little bit more involved. We okay? Now, I asked you to take out Desmos test mode and put it on your phone. So let's see here. Let's see. Desmos. Here we go. You should see this one. This is what you're looking for, Desmos test mode. So if you open up that, you could make your life a little bit easier. Now, I'm not going to do it here because it just doesn't display as well. But what I want you to do is practice using this. And to get going here, you're going to click this one. I think it's already selected. And then do Start Practice. Now what's going to happen is that's going to start a timer. And as long as you're on this app, that timer is going to keep running. So what I could do is I could start everyone at the same time, and then when you're done with the test, you bring me your phone and show me your phone, let me press the done button, and then I can see how long you've been on the app. If the test started at 10 o'clock and you hand it in at 10:45, the little timer should tell me you've been on the app for 45 minutes. That means you didn't leave it and go to ChatGPT or Photomath or something like that to solve your problems. That way I can test you and allow you to use your phones as well. Now what's the benefit of that? Well, the benefit of that is you can graph these things pretty nice. For instance, what does the graph of x less than or equal to y look like? A lot of you might not know. So we'll hit the y key here, and then less than or equal to is right next to that. Y is less than or equal to x, and bam, There you go. That's kind of nice. Let's finish this up here. And let's see. I'm just going to open up a new Desmos. Now, one thing I want to point out here about our constraints. There's two constraints that you can look for that could make your life a little bit easier. What two constraints do you think I'm talking about in this particular problem? Actually, those two. What's special about those? Liv? Suggestions? What's special about these? What does that tell me about my solution?
It's letting us know which quadrant we're working in.
Yeah, this is going to be your first quadrant. So I'm not going to worry about anything outside of the first quadrant. I'm just going to worry about this much. And in fact, you can use Desmos to try and find some of these other things. For instance, I want to know where x plus 5 is less than or equal to, or excuse me, where x plus y is less than or equal to 5. So, wrong one. How about this one? So, x plus y is less than or equal to 5. Now, I'm going to get a little bit fancy here. I don't want to see all this other stuff outside of the first quadrant. So I'm going to put in a couple constraints like x has to be greater than or equal to 0, and same with y. But there we go. So there's x plus y is less than or equal to 5. A lot of times I'll color these orange so that way I can layer several of these on top of each other. What else? I want to know where x plus y is greater than or equal to 1. Okay, so let's do that one as well. So type in x plus y is greater than or equal to 1. And again, I'm going to color that one orange. And I'm going to borrow these constraints as well. There we go. So right now you can see where these two regions are overlapping, right? They're overlapping in this little stripe right here. That's fine. But there's one more constraint here for us, and that's the line x plus y is, let's see, no, x is less than or equal to y, or y is less than or equal to x. Y is less than or equal to x. I'll put in these constraints. Like I said, I keep everything the lightest color. That way, when they're all overlapped, you can see the feasibility region. It's right here. So let's kind of color that part in. So it's going to be here. Now, I haven't really decided how I want to write the exam on this part. I mean, one way I can do that is to give you these coordinates and then let you figure out which region gets shaded, and that way you only test the points that you need. Or I could just let you do the whole thing, you know, from scratch. But certainly with Desmos, this becomes a little bit easier. Let's kind of zoom in here. We've got points at 2.5 and 2.5, 0.5 and 0.5, 1 and 0, and then 5 and 0. So those are the corner points that you're going to have to test. This one, this one, this one, and this one. Those are the points you're going to have to test in your feasibility region or into your objective function. Now, if you're looking at that going, that's a lot of points to solve for. Well, there's one other thing we can do with Desmos to make our life a little easier. Right now, it won't click and let me solve these equations. But if I turn these equations, or excuse me, inequalities into equations that make that an equal sign, then I'll be able to click and solve for where these things overlap. So I guess it depends up, you know, it's up to you how hard you want to work on solving some of these things. But I'll just make these all equations. Now the cool thing is I can just click here and find where these points overlap. So nice. those are the 4 points for my feasibility region, the vertices. Let's see if we can't figure out where the max and the min is. Before I do that, let me pause. Are we okay with what we got here? Aurora, you look a little unsure. What can I help out with?
No, I think I get it. I'm just.
Yeah, it's a lot. So let me kind of recap here. So the first thing I did was I graphed these inequalities and determined that this part here was my feasibility region. Okay. And then, in fact, I can shut these off. I graphed the corresponding equations, and now I can click and see, well, where do these things overlap? So that gives me the points, the corner points of my feasibility region. Now, finally, I'm going to test those points into my objective function. So what was our objective function? Our objective function was this right here, 1/2 x plus 1/2 y plus 40. Okay. You can, if you want, plug that in decimals. N of x and y equals 0.5x, which is your 1/2 x, plus 0.25 y plus 40. Okay. Now I'm just going to plug in those different values. So the corner of the vertices, let me see if this will stay up here. No. Darn it. All right, so let's try over here. Yeah, that figures they vanished. N of 2.5 and 2.5. That gave me one answer. And then we had N of 0.5 and 0.5, gave me another answer. And then we have 2 more points, N of 1 and 0. And finally, N of, let's see, 5 and 0. Great. So let me write all those down. You can copy those down. Let's see.
Mr. Barrett,
Yes.
I'm putting in the same lines as you, but I'm not getting the same thing.
Putting in the same lines.
Do you need the part in the parentheses?
No, you don't need the part in the parentheses.
Because I put in x plus y equals 5, and it gave me a different line than what you have.
X plus y equals 5 should go through these 2 points. Is yours not going through those 2 points? Something feels a little wrong. It should go through those 2 points. And then, we'll see.
They're all just going through 0.
Bring it up here. Okay. While you're bringing that up here, let me copy down these answers. Let's see, we've got N of 2.5 and 2.5. Oh, it's because you're zoomed way out. This is like in the scale of 5,000s. Hit the home button. Zoom in. You were zoomed out. You were looking at something. Your x coordinates were like 5,000. So that no, your graph was right. It just you were just zoomed way out.
Thank you.
All right. So 2.5 and 2.5 gave us 41.875. 41.875. Doesn't feel right. Yeah, I guess it is. All right. And then N of 0.5 and 0.5. Gave us 40.375. N of 1 and 0. Gave us 40.5. And N of 5 and 0. Gave us 42.5. So we're asked to try and find the maximum and minimum values. What's the maximum value? Oh, sorry. Yeah. Zoom out. There we go. What's our maximum value?
42.
Yeah, 42.5. That's our max. How about the minimum value? Yeah. 40.375, that's your min. Nice. Nice. Okay. Done with that one. We're going to practice a couple more. I want you to get used to using Desmos a little bit. You don't have to use Desmos on the exam. You just don't. It's just going to be an option that's going to be there for you. I think it makes this problem a lot easier. Without Desmos, these are like 10 to 15 minute problems. With Desmos, they're like 5-minute problems. So it's up to you. You don't have to use it. But I do caution you, make sure that I'm the one that shuts off Desmos. I want to press that button. You know, this is going to come as a shock to you, but people have figured out a way to cheat. They take screenshots of their phone, you know, with different times, and they just pull it up and say, oh yeah, look, see, I've been on it for 40 minutes. And it's just a screenshot. So yeah, so I'm the one that has to press Desmos. Okay. Any other thoughts on example B? We're starting to get into the swing of these things. Let's try example C. Now example C is one of these where you're going to have to kind of set up your own constraints. So we're kind of stepping things up a little bit. Furniture manufacturer makes wooden tables and chairs. The production process involves 2 basic types of labor, carpentry and finishing. A table requires 2 hours of carpentry and 1 hour of finishing. A chair requires 3 hours of carpentry and a half hour of finishing. Here's all the stuff about the profit. The manufacturer's employees can supply 96 hours of carpentry work and 20 hours of finishing work per day. So, okay, let's try and put things together. And that is, starting with a table requires 2 hours of carpentry. 2 hours of carpentry. And a chair requires 3 hours of carpentry. How much time do we have to spend on carpentry altogether? 96 hours. So all these things are color-coded to go together. Okay. So for our tables, we have 2 hours of carpentry. For our chairs, we have 3 hours of carpentry. We have 96 hours of carpentry to work with all together. So that's where our first constraint comes from. What else is constraining us? Well, we've got some finishing work to do. Hour of finishing for a table, half hour for a chair. Okay. How much time do we have to spend on finishing work per day? 20 hours finishing work. And that gives us another constraint. And that's it. That's all I've listed for constraints. But somehow or another I put 2 more constraints here. Why? Where are these constraints coming from? They weren't in my problem. What's going on? Do I just throw those in there just for good measure?
You can't spend negative hours on something.
Thank you. You can't work a negative amount of hours on finishing or on carpentry. So these are called the natural constraints. They arise naturally. Natural constraints. Leo, what are the natural constraints? Tell me about my solution.
It has to be in the top right quadrant.
Yeah. So we're just going to graph things in the first quadrant. Now, you don't always have to have those natural constraints. It could vary depending on the problem. But yeah, spot on. Thank you so much. Then you've got to graph these things. So, okay, let's graph them. Now, suppose you're not interested in using Desmos. What you could do is graph them with just plotting some points. So let me plot some points for this one. So I'll put in t and c. If I put in t equals 0, that gives me 3c equals 96 or c equals 32. If I put in c equals 0, I get 2t plus 0, or just 2t equals 96. So t would be 48. Okay. And those points look like they're right here and here. Here and here, that would be 48 and 0. And this would be 0 and 32. I can do likewise for the next one as well. So we'll do a little t-table for that one. T and c. If I put in a t equals 0, then I get 1/2 c equals 20. Multiply both sides by 2, I get 0 and 40. So that's going to have to be this one up here, 0 and 40. If I put in a c equals 0, then that's pretty easy. I just get 1t equals 20 or t equals 20. Nice. So you don't necessarily have to use Desmos on these things. Is it convenient? Sure. Sure, I get it. It's going to be up to you. So here and here, those are our graphs. Where are you going to end up shading? Well, we got to do that work ourselves. And let me just go through it by hand just to show you that you don't necessarily always need to use Desmos, but you can. So we're going to test, I don't know, any suggestions as a test point? 0, 0. Yeah, 0, 0. Thank you so much. Every now and then I get somebody that says like 7 and 17 or something like that. I'm like, well, you could. All right, we'll test 0, 0. If I test 0, 0 in this inequality, 2 times 0 plus 3 times 0, is that less than or equal to 96? Yeah. Now I'm testing this inequality, and it's telling me to shade below. All right, great. Let's test the other one. So that was for my yellow inequality. Let's test the orange one. So I'll test 0, 0 again. Is 0 plus 0.5 times 0 less than or equal to 20? Yeah, that one's again true. So shade below. So it's going to be below here and below here. What you have to do now is you have to decide, well, where do these things overlap? And they're going to overlap. And I probably should have given you a second to try this yourself, my bad. They're going to overlap right there. That's your feasibility region. Okay. Fair enough. Now, from our feasibility region, I'm going to need all the vertices. Fortunately, the way we graph these, we've got most of these vertices. That's going to be 20 and 0. This is going to be 30 or 0 and 32, 0 and 0. We kind of know that one. But then there's this one. How are we going to find that one? You can get kind of an idea of what it is by the graph, but it's not perfect, is it? I think there's a couple easy ways to do this. One is to set up a system of equations and solve it by the addition method or substitution method. And the other one is graphing. So I'm going to bail out here and use Desmos on this last one. So let me shut off some of these. And then I'm going to type in x instead of t, y instead of c. So I'll get 2x plus 3y equals 96. And 0.5x, just double check here. No, x plus 0.5 y equals 20. And boy, I don't see anything. What's going wrong? I don't see anything.
You zoomed in too far.
Yeah, I'm zoomed in too far. So if you zoom out a little bit, eventually you'll see where those two lines overlap. It's going to be at 6 and 28. 6 and 28. Wonderful. So put that point in there. There's one last thing to tend to. How many tables and chairs should be made each day to maximize profit? What was the profit? How much profit are you making here? Oops, wrong way. Well, we need one more thing here. Profit is $35 per table and $20 per chair. All right, I really got to update this. This feels way out of date. I hope those numbers are woefully short. But we could do table and chair. Let's see, P of T and C is going to be $35 per table plus $20 per chair. Okay. Now I'm going to do a little experiment here. I think I can get away with this. I'm going to build my function Desmos with T and C as opposed to X and Y. I think it'll still work. It should still work. We'll find out. If it doesn't work, blame Desmos. So we'll shut those two off. And I'll do P of T and C equals, equals 35T plus 20C. Okay. So far, so good. Seem to accept that. What points should I be testing?
0, 32, 6, 28, and 20, 0.
Nice, thank you. So P of 0, 32, P of 6 and 28, and P of 20 and 0. Nice. So the one that maximized my profit was 6 and 28. Please don't always think that it's always going to be this one, at least for the exams. All I need to do is change this function a little bit, and the maximum can shift to any of these corners, depending on my whim. So do be conscientious and test all the points. Don't necessarily assume that it's just going to be that one and you're done. Okay. A lot on that one. How's that one looking there? Yes, please, Zandos.
How do you get the number 6 and 28?
So 6 and 28 is where this line right here, which is 2t plus 3c equals 96, and this line right here, which is 1t plus 0.5c equals 20, it's where those two lines overlap. So the intersection point where they meet is your solution there. And for that, I just graphed it. I just said, you know what? I could solve that by substitution or addition, but I got lazy. I wanted to get done with this problem, so I just found it on Desmos. Liv?
What unit is this?
It's just called linear programming. It's not a particular section number. It doesn't, I mean, at one point, this was in a book. Now you got it in an ebook, so you don't necessarily see the chapters and stuff like that. But even back then when it was a book, it was an appendix kind of topic. So it doesn't have a section number like some of the other stuff does. But there still should be some homework for it though, which is a good thing.
Where?
On D2, on WebAssign. Is it not there?
I don't know.
All right, well, I'll fix that. I'll make sure that, you know, you have something to keep busy with over the weekend. Blake?
When you're figuring out the dollar amounts on Desmos, is that P in front? You always have to have that there? Does it mean like profit?
Yeah, that,
profit, I
well,
guess?
you could give this any variable you want. I could call it B for Blake, and then I'll just use the same thing here. It's just the name of it. Yeah, so I happen to use P for profit, but if you're partial to B for Blake, that works as well. It's just the name of your function.
I see.
Yeah, no, great question. Thanks so much. Will, any questions? No? Okay, all right, good. Let's see. I think we got time for one more. Let's see. Part of your challenge in this is going to be setting up the problem, or setting up the inequalities and stuff like that. So, if you'd like, we can finish. Yeah, maybe we'll do 2. We'll just do the setup for example E, and then maybe we'll do example D or F, depending on your mood and depending on our time. But again, the point of these problems is that you're working under constraints. Now, this subject has progressed a lot during the years. You can actually get a degree in stuff related to this kind of thing, and that would be, I think a systems analyst does linear programming, a lot of linear programming, and that's a pretty well-paid job. So, yeah, this kind of stuff does turn into careers. There's a guy by the name of Carl Marker who decades ago came up with a better method to help solve these problems, and I think he's probably pretty rich by now. That is assuming he's still around. Okay, a trucker hauls fruit from Florida to Montreal. Each crate of oranges is 4 cubic feet in volume and weighs 40 pounds. Each crate of grapefruit, which is our Y value, has a volume of 6 cubic feet and weighs 50 pounds. This truck has a maximum capacity of 300 cubic feet and can carry no more than 3,200 pounds. So, sounds like his F-150 or maybe a Dodge 1500. Not a big semi. Moreover, he's not permitted to carry more crates of grapefruit than crates of oranges. And then they talk about his profit. So there's a couple constraints working on things here. Now I've called oranges, or crates and oranges, the number of crates and oranges we have is X, however many crates we have. And let's see, each crate of oranges has 4 cubic feet of volume. Okay. How about grapefruit? How much volume does a crate of grapefruit take up? 6 cubic feet. So Y, 6 cubic feet. How much do we have altogether in terms of cubic feet of capacity? 300. So that's going to lead us to one of the inequalities. What's something else that constrains us in this problem? Well, that we already did the volume. What else? The weight. The weight. 40 pounds for each crate of oranges, 50 pounds for each crate of grapefruit, and we can carry no more than 3,200 pounds. So my challenge to you, and I'll let people pause the video if they're watching it later, is to try and come up with a couple inequalities that represent what's going on here. Okay. Let's see how we're doing here. Let's first of all set up the inequality for our volume. And it seems like my yellow marker is on the way out. Let's try this one. Oh, that one looks a lot better. Okay. So what's inequality? What's an inequality here? Dom, in back.
4x
Mm-hmm.
6y is less than or equal to 300.
Perfect. Thank you, sir. And Dom, how about another inequality for our weight?
40x
Mm-hmm.
plus 50x plus 3200.
40x plus 52y, 50y is less than or equal to 3200. Great. Somebody give me two more inequalities.
X is greater than 0, y is equal to 0.
Ah, beautiful. You've got your natural constraints, right? X and y are both greater than or equal to 0. You can't carry less than 0 crates of oranges or 0 crates of grapefruit. So x is greater than or equal to 0 and y is greater than or equal to 0. Those are kind of implied. They're not said. They don't have to be said. There's one last inequality here, though. And I'm kind of running out of colors. Let's see. He's not permitted to carry more crates of grapefruit than oranges. So that's one last inequality. He's not permitted to carry more crates of grapefruit than oranges. So it's kind of a strange constraint. We haven't seen that one before. What would that be? Yeah, x is greater than or equal to y. So that the number of crates of grapefruit is less than or equal to the number of crates of oranges. So x is greater than or equal to y. Beautiful. So, wow, you've got a lot of inequalities here. Really, this just tells you you're in the first quadrant, then you got to deal with the rest of these three. Last but not least, let's see. His profit is $2.50 on a crate of oranges and $4 for a crate of grapefruit. God, I gotta update these numbers. They feel so out of date. Let's see if we can't write a function here. And I'll use P for profit again of X and Y. So $2.50 a crate on oranges. So that's 2.5x plus 4y. That would be your objective function for something like this. So, yay. Yay. You're all set up now. You can do the rest. Now I needed to ask you an important question. Do you want to do either D or F to finish this off, or are you feeling pretty comfortable with these? It's up to you. Do it? All right, let's do it. Tell you what, just to, in the interest of time, let's do kind of an easier one here. We start out by noticing this much. Lena, what's this much tell us? X and Y greater than or equal to 0. What's that tell us? Yeah, first quadrant. Those are your natural constraints. Great. Let's see if we can eyeball these things and determine which line is which. So I'll make this one orange. Let's see. So for that one, if I made that one orange, let's do that over here. X and Y. I've got 2x plus y equals 14. If x is 0, y is 14. If y is 0, I get 2x equals 14, so x equals 7. So I get 0 and 14, and then 7 and 0. That looks like these points up here and down here, respectively. So 0 and 14, 7 and 0. Let's just draw a nice straight line here. Now, it's not necessarily a waste of time to try and figure out these coordinates as well. So let me do that. So that's going to be for this equation. 2x plus 4y equals 52. X and y. Again, you're going to put in 0 and 0. If I put in a 0 for x, I get 4y equals 52. That's going to mean y equals 13. If I put in a 0 for y, I get 2x equals 52. So that means y is going to, or x is going to equal to 26. So this point here, 0 and 13. And then 26 and 0. How about if we finish this one up on decimals just for the practice, just so that you're comfortable with some of this thing. Let's see, let me get up a new graph. Oops, there we go. So let's see, I want to graph 2x plus y equals 14. Do I have those? No, I don't. And I want to do that for x is greater than or equal to 0, and likewise for y greater than or equal to 0. There we go. So that's one of them. If you click the tool icon and this larger A, it makes things a little darker, a little bit more visible for you. What else do I need? I need 2x plus 4y is less than or equal to 52. I'll start out with 2x plus 4y equals 52. And again, let's put in those natural constraints. Now, why did I graph the equations first using decimals? Can anyone suggest a reason? When you graph the equations, you can do this. You can click on a point of intersection, and it'll tell you what that point of intersection was. Will, do you like that feature? No? Yes? All right. And in fact, if you're looking at that going, yeah, but those are decimal values. Well, I don't know if the app does this or not, but you can click this, and it'll put it over here. Does that? Yeah, no, it's not. No, I was hoping I'd get the math button that allows me to turn that into a fraction. But maybe you recognize that. What fraction is 0.6666 and then 7? 2/3. So that's going to be 2/3 there. And then it looks like 12 and 2/3. 12 and 12 and I don't know, 12 and 2/3. I guess I can't get away with it. I just have to write 37 over 3. All right, so there's, no, how about, no, that wasn't right. 12 and 2/3 would be 24. Why am I missing this? 12 and 2/3. Oh, 38 over 3, right?
Yeah.
38 over 3. There we go. There we go. So those are the exact coordinates. Then we've got this one. Actually, I guess we need to figure out where we're going to shade here. Now, the nice thing about decimals is it can do those testing of points for you. So I'm just going to copy this down here and paste it. Turn that into an inequality. That first one has to be a less than or equal to. Likewise, we're going to do the same thing with this one. Let me change the color on that. And I want to make this one a less than or equal to as well. And we can see where they overlap. They overlap in this region that's closest to 0, 0. So here. And let me get rid of the shaded part so I can click on these points. There, there, there. All right, so these are the test points I'm going to want. 0 and 13, 2/3 and 38/3, and 7 and 0, 0, 0 as well. Blake, give me your favorite letter. P? All right, P. So we'll do P of X and Y. And the objective function in this case is a little bit simpler than some of the ones we've had before. 140 minus X plus 3Y. So equals 140 minus X plus 3Y. And now we can test our points. So 0 and 13, that'll be one of them. P of 0 and 13. P of 2/3 and 38/3. And finally, the last one was what, 7 and 0? Yeah, 7 and 0. P of 7 and 0. Nice, nice. Of course, you could put in P of 0 and 0. That would give you 140, right? Oops. P of 0 and 0. So that's interesting. P of 0 and 0. Wait a minute. Why is that looking wrong? Oh, okay. Yeah, all right. Makes a big difference. Our minimum point is no longer at 0, 0. Our minimum point is actually at 7 and 0. Our maximum point looks like it's at 0 and 13. So this point right there, that's going to be the maximum point for this objective function. Nice, 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 nice. Okay, I'll let you copy down these numbers, but that's all we got for example D and linear programming. Any thoughts or comments before I wrap this one up?
How did you make it give you the number?
You mean the maximum or minimum points, these values?
Yeah, how did you get, like,
I had to define this function, so I had to write it all out, so I just typed that in. So let me type in a different one. I'll just type it in L of X and Y equals, and then I can do 140 minus X plus 3Y. So it's whatever name you want to give it. If you want to give it an L for some special reason, that's fine. But then you just type in the function, the format of the function, and then you can put in points. Like I could change that to L, and it shouldn't change the value here. So, because it's just using the same formula. If I change this a little bit, like make it a 2, you'll see that value change. Because now it's taking 140 minus 0 plus 2 times 13 is 166.
one other question.
Yeah, please.
For the decimal, the fractions one, how did you get it to become fractions?
I had to figure it out. I had to look at that and go, you know, that looks like 2/3. So yeah, sorry. I was hoping there was to be a nice trick. Sometimes, depending on the problem, like for instance, suppose I put in 13.25 here, then it gives me this answer of 166.5. But the cool thing is if you hit this little button here, it says, oh, you want that as a fraction? I'll give it to you as a fraction. Or if you toggle back, it gives it to you as a decimal. So unfortunately, it wasn't available to us in this one. But I'll tell you what, a couple of my favorite teams are doing pretty well. So that means probably over the weekend when I write this exam, I'll be in a good mood and I won't give you anything that gives you a nasty fraction like that. All right, fair enough. Anything else? Okay.